Hello students, welcome to the class. So today we will see the theory part 7 of the chapter chemical bonding and molecular structure. So we have already started the topic valence bond theory. In this we will continue that section, which is section 4.5 of the NCERT. So this is the disclaimer. If I talk about today's objective, then it would be mainly about predicting the directional properties of covalent bonds. Okay. So we will see that how the atomic orbitals combine when the atoms come together to form a bond. Then if I specify the sections that we are covering today, then those are orbital overlap concept. Second is directional properties of bonds. Third is overlapping of atomic orbitals, types of overlapping and nature of covalent bonds. And lastly, strength of sigma and pi bonds. So these are the 5 topics that we will see today. So let us start with the orbital overlap concept. So we have studied it in the previous class that for the formation of hydrogen molecule, we are to bring two isolated hydrogen atoms together, and at a point their potential energy is minimum, and we call them as the formation of the hydrogen molecule. Now this is the overall energetics part, but what is happening with the atom? What is happening to its atomic orbitals? We will discuss that part today. So whenever two hydrogen atoms come closer to each other, then their atomic orbitals overlap partially. Now overlap meaning means it is simply, you can say, think of it in a way that they are mixing together, right? Overlapping means they are on top of one another. So whenever two hydrogen atoms come together to form a bond, their orbitals, so which would be obviously 1s orbital, so 1s orbital of both the hydrogen bond, they overlap with each other partially to make the bond. Now this overlap is the reason why your energy is decreasing. So we have seen it in the previous class that your energy was decreasing as you were moving from two isolated gaseous atoms to a complete molecule. The reason behind the fall of that potential energy is the overlap of the atomic orbital. And we know that this minimum energy state was obtained at a distance of separation of 74 picometer. And due to that minimum energy, your molecule was becoming stable. Okay. Now we know that two atomic orbitals are combining here. So there must be some change in the atomic orbital, changes in their energy, change in the shape. So our discussion will be totally focused on that part. So till now we know that if your two hydrogen come together, then their energy go on decreasing, and during this whole process, the atomic orbital of one hydrogen atom overlaps, or you can say they are on top of one another, and they are coming closer and closer until and unless they get a minimum energy, and it is at 74 picometer for the hydrogen molecule. Now this partial mixing or merging of this orbital is called as orbital overlap. So we can define orbital overlap in this simple manner, that the partial merging of the atomic orbitals is called as orbital overlap. Now remember students, we will always tell that your merging is partial. So it will never happen that your two atomic orbital will be merged completely. A part of the atomic orbital will merge with the another part of the atomic orbital, and that will result in a bond. You will understand this thing whenever you will see the diagram. So in this will come in the upcoming slides. So for right now, you should remember that partial merging is the reason behind the formation of bond, which is happening as a result of orbital overlap. Now, what is happening inside the orbital? So inside the atom, your orbitals are mixing. But what is happening inside the orbital? So basically, we take such two orbitals which have one electron in them. Okay, so if you are taking two different orbitals, each of these orbital will have one electron, and after the mixing, or you can say overlap of these two orbitals having one electron, you will pair up the two electrons present in the individual orbitals to form a complete bond where your both of the electrons are now paired up. So we can say that during the overlap of two orbitals, the two orbitals have one electron, and whenever these two orbitals combine, the two electrons get paired up with each other. I hope this is clear to you. Now, remember, after the pairing up, the electrons that are present in that overlapped region will have opposite sign, and this pairing of the electron is the reason for stabilizing the bond. Okay. Now, if I talk about the strength of covalent bond, it depends upon the extent of orbital overlap. We know that the overlap is not complete, it is a partial merging, and greater is that merging, or you would say greater is that orbital overlap, more stronger will be the bond. And which type of bond? So greater overlap results in a stronger covalent bond. I hope this is clear to you. So what we got in this whole slide? So we were discussing earlier that we bring two hydrogen atoms together to form a complete hydrogen molecule at a minima of energy. Now inside the atom, whenever your two atoms are being placed together, their atomic orbital combine with each other, and these atomic orbital contain one electron each. When these two atomic orbitals combine, or they merge, or they overlap, these two electrons get paired up. Okay, and we get the final chemical bond, or the strong covalent bond. Now we'll try to explain all of this process in more minute manner, that which orbital will overlap with which orbital and what will be the effect after the overlap. Then we'll talk about different orbitals giving different extent of overlap. So moving on to that, three overlaps are possible. Okay, so after overlapping, three conditions are possible. The first condition is positive overlap. What happens in the positive overlap? If you look in the diagram, then 3 to 4 types of positive overlap are being mentioned here. In the first case, two py atomic orbitals are combining. Okay, and remember students, if you look at the sign which are being merged together, so you can clearly see that there is not complete merging. Okay, only a small part of the atomic orbital is merging with the other orbital. Now if you look at the sign of the atomic orbital, then same sign overlap to form the positive overlap. Okay, so this is very important. For the formation of bond, there must be positive overlap. Okay, without positive overlap, formation of bond is not possible, and that thing only happens when your two atomic orbitals are combining in the same phase. Phase means having the same sign. Plus and plus are combining with each other of py. Similarly, minus and minus of py are combining in the down part. Similarly, you can think of the px orbitals. So here you can see that two px orbitals are combining with each other in the same phase to give the sigma bond. Then coming on to the third picture, this overlap is not among the same kind of orbital. Okay, instead of that, we have overlap between a s subshell and a p orbital. Okay, simply say s orbital and p orbital. Here also your s orbital will have a positive wave function or positive sign of wave function. So your pz orbital will also combine with its positive lobe. Now this positive lobe can also go on merging with the pz orbital itself. Okay, so these 4 types of positive overlap are possible. Now, again, this will be classified into further small parts. But for now, you should remember that how different types of orbitals can combine. In the first case, 2 py orbitals are combining. In the second case, 2 px orbital are combining. And in the third case, 1 s orbital and 1 pz orbital is combining. Now, here is a very, very important thing. And that thing is, why the ps orbital is only capable of doing this kind of overlap? Because if you look at these 3 diagrams, okay, about the p subshell or the p orbital specifically, then you would notice that the py px are merging through 2 points of contact, one on the positive, one on the negative. Similarly for the px also. But in the case of pz, there is a different kind of overlap that is being seen. So remember, this is very important to understand that your pz has a different kind of overlap. We will talk about that what is the consequence of this. Now coming on to the sign of this orbital, remember students, this sign is never representing your actual sign. Okay, so this is very important to understand because they are representing your atomic orbital, of course. So as a result, if they are representing your atomic orbital, means they are representing your probability of finding the electrons, and we know that your electrons are always negatively charged. So there is no question of having a positive charge on the orbital of electrons. Is it clear? So you will not make confusion, or you will not create confusion by yourself that since the 2 orbitals which are combining are having the positive sign, so they would repel each other. They would never repel each other. This positive and negative sign, they are just representing the wave function condition. You must have seen a wave function. There you have positive and negative amplitude. Here also you have this same thing being described here. That your positive and negative are the amplitude of this given wave function. Okay. I hope this is clear to you. Now these 4 diagrams are very, very important to understand the concept of hybridization. So please remember this. Okay. Now moving on to the next type of overlap, which is negative overlap. What is the difference between the positive and negative overlap? So basically, in positive overlap, same phase of the atomic orbitals combine. Whereas in the opposite overlap, or in the negative overlap, different sides of the orbitals are combining. You can see it in the py overlap, that your positive is combining with the negative or overlapping with the negative. Similarly, the negative of the other is combining with the positive of the other. So this is not feasible for the formation of bond. Only the positive overlap is possible. Therefore, this kind of overlap is being rejected. Similarly, if you look at the px, if you are taking the opposite orientation, then again you are getting a negative overlap because the positive is combining with negative and the negative is combining with positive. Same thing is true for the PZS orbital. You can see it here that the negative part, or you can say the negative amplitude of the PZ wave function is combining with positive part of the S orbital. Similarly, your PZ is combining with the PZ. So this is the overall picture of the overlap that we are discussing. And it's very important to understand, right? Now you can see one thing very clearly, that your PZ orbital is only doing the different kind of interference, or you can say different kind of merging. Why? Because your atoms are approaching through the Z axis. If you look here, then your 2 atoms are combining through the Z axis. Okay, and that is the reason we are only getting a different kind of overlap for the PZ orbital. So this is very important to understand. Now moving on to the next kind of overlap. So that next kind of overlap is zero overlap. Now, what is the meaning of this zero overlap? If you look at the diagram here, you can clearly see that a positive, or I would say a positive wave function of the s orbital is combining with the negative wave function of p orbital. What will happen as a result? It will result in a zero overlap. Okay, so this is very important to understand that when is the condition we do see a negative overlap. Similarly, if you consider the next overlap, it is between px and py. So the same thing is applicable for all kind of what? All kind of different orientation overlap. Like if you take the px and py, or you take the py and pz, or you take the px and pz, there will be always a zero overlap. Right? I hope this is clear to you. It's very important to understand that why is the zero overlap occurring. Now let us move to different kind of overlapping, and that will depend on the nature of covalent bond. So let us try to understand that part. So what is the number of sigma bond here? So it's very easy. Sigma bond are formed by the head-on-head overlap of the bonding orbitals. Now what is the meaning of this head-on-head overlap? Whenever the overlap is along the internuclear axis, then that overlap is named as head-on-head overlap. Now what is the meaning of this internuclear axis? The axis which connects nuclei of two atoms. Okay, so that would be a good example of the internuclear axis. Now the sigma bonds are formed by three kinds of overlap. We said it earlier that the overlap which is formed by the head-on-head overlap is called as the sigma bond, and it is formed by the following combinations of the atomic orbital, and those combinations are SS overlapping, SP overlapping, and PP overlapping. So these are the three kinds of head-on-head overlap that we will see today for the sigma bond. So first, let us talk about the SS overlapping. We know it very well that during the combination of two atomic orbitals, they have one electron in their orbital, and they do combine to form the complete paired up electron. Okay, so this is very important to understand that whenever two s orbital combine, then both of these s orbital have one single electron that on combination give a paired up electron, and this whole thing is occurring along the internuclear axis. Now this head-on-head overlap results in a very good sigma bond. Okay, you can see the diagram here. If you look at the diagram, you can see that there are two spheres which are differentiated from each other or kept apart from each other. In this case, your sigma bond, okay, is being formed because the s orbital are overlapping head to head, and they are overlapping along the internuclear axis. Okay, so this line which is passing through the center of each of this is called as the internuclear axis. Okay, so I guess this is clear to you. Now this overlap is happening due to the head-on-head overlap, right? And this thing, head-on-head overlap, results in the sigma bond. Now similarly, this same sigma bond can be seen for the sp overlap. How? Again, what will happen? We will take a s orbital which is half filled, and we will take a p orbital which is half filled, and then we'll do the head-on-head overlap to create the sigma bond. And how does this overlapping look like? So you can see it very clearly here that we have a s orbital that is combining with a p orbital, right? And overall, upon the overlapping, we are getting the sp overlapped thing. Now what is common in between these two kind of overlapping? That they both are overlapping along the internuclear axis, and there is a head-on-head overlap. Remember students, again this p orbital would be which orbital? It will be z, because we are taking the z axis as the internuclear axis. So remember students, whenever you see a different axis for the internuclear axis, do not take the pre-assumed things, okay? Because in that case, your configuration can change. So remember this point, that your overlapping, P overlapping, is with the S overlapping, and it is happening along the internuclear axis, which is Z. Therefore, the S will combine with the PZ always. Okay? The S will combine with the PZ always, because S is having what? S is having a overlap with P due to the Z. I guess it is clear to you. Yes, there is a chance of overlap between S and D also. There is no doubt in that. Of course, S combines with S combines with P, and S combines with D. But the point here is that which orbital should combine, because a D orbital are of various types. D are dxy, dxz, dyz, dx square minus y square, and dz square. If you are understanding this point clearly, that why S and PZ are combining, then you can easily say that out of these 5 d orbitals, which will combine with the s orbital to form the sigma bond. So I am leaving this question to you. Again I am repeating that question. You know that since the p orbital is aligned along the z axis, therefore it is capable of forming the sigma bond with s, as the internuclear axis is z. Now if I ask you, out of the 5 d orbitals, which d orbital is the most capable of making your sigma bond? So your answer would be what? So there are 5 orbitals: dxy, dyz, dxz, dx square minus y square, and dz square. Okay. So dz square would be the correct answer. So you can go and look back at the structure of the dz square. Your dz square is oriented along the z axis, and your pz is also oriented along the z axis. If you bring it with the s orbital, then both of them are capable of forming the sigma bond. So correct answer will be dz square. Now moving on to the next. So the next type of overlap is PP overlapping. What happens in the PP overlapping? Now PP overlapping can be of multiple types. Obviously, in this part also, your 2 p orbitals, which are having 1 electron each, they will come and join along the internuclear axis to pair up their electron. Again, we will talk about the PP overlap, which is resulting in a head-on-head overlap. So this is the diagram for that. You can see that there are 2 p orbitals, and they are combining together along the internuclear axis Z to form a sigma bond. Now my question would be that which p orbital is moving along this axis to form the what? To form the sigma bond. So there are px, py, and pz. So which orbital is perfect for the formation of the sigma bond, given that your internuclear axis is Z? Okay. So remember, students, this is very important point. Whenever you are deciding that which orbital will form the sigma bond, the most important part is that whether or not it is mentioned that your internuclear axis is Z or not. So this is most important part. If it is mentioned, then go without any hesitation that the correct answer will be PZ. If it is mentioned as PX or PY, then in that case, your sigma bond will be formed between 2PX or 2PY. Okay, I hope this is clear to you. Now moving on to the next, which is pi bonding. So we have seen 3 types of sigma bonding, which is between SS, S and PZ, and PZ and PZ, if the PZ is the orbital lying along the internuclear axis. Now let us move on to the formation of pi bond. So unlike your sigma bond formation, this pi bond is formed by a side-on-side overlap or a lateral overlap. Now this is very important to understand that what is the meaning of this side-on-side overlap. Again, if you look back at your previous slides that I have taught you in the lecture, you can clearly see that there were side-on-side overlap between the p orbitals, apart from the direct head-on-head collision. So, the first overlap will be between px and px, and the second overlap will be between py and py. Remember, students, your formation of pi bond with px and py is only possible if both px and py are along z-axis, and that z-axis is the internuclear axis. Remember this point. This is very, very important. If your internuclear axis is changed to x, then your px will be the one forming the sigma bond, whereas your py and pz will form the pi bond. Okay, so this is very important to understand. Now, in this kind of overlap, the orbitals will have their same spin, but this is parallel to the say overlapping and perpendicular to the internuclear axis. Okay, so axis of overlapping atomic orbitals are parallel to each other, whereas perpendicular to the internuclear axis. Let us try to understand the same with the diagram. Say we have two px orbitals that are combining, and in between we have an internuclear axis. Okay, now as these two orbitals are moving along the z-axis, therefore these two atomic orbitals must be px and py. Okay, suppose these are px, then it will combine to give you this final diagram. Okay, is it clear? So I hope this makes sense to you. Now 2 points are important here, which are very noteworthy, that in case of the side-on-side overlap, the axis of the orbital is perpendicular to the neutral, whereas your axis of orbital is perpendicular to the internuclear axis. Okay, and this overlap results in a special type of the final atomic orbital, or you can say it overlapped orbital. Now, what is the characteristic of that pi bond? That it is formed by the side-on-side overlap, and the overlapped orbital have a saucer-shaped like structure. So here is the image given of that. You can see two saucers are there, which are below and above the plane, and these two saucers are representing your what? They are representing your lobes, where the electron density is maximum. So as I have told you, there's this two saucer shaped like electron density, which have very high electron density along this axis. Got it? So I hope this is clear to you, how a pi bond is formed and what are the position of internuclear axis and the axis of the orbitals as well. Now let us try to compare these two types of sigma and pi bond. Okay, so we'll try to compare both of this. First of all, we know that the strength of a bond is totally dependent upon the extent of orbital overlapping. So this is the most important part. Greater is the overlapping, more stronger is the bond. Now if I take the case of sigma bond, then it is seen that the orbitals overlap to a very greater extent. Okay, if they're overlapping head on head, or you can say if they're forming the sigma bond, and this thing is seen naturally. And this sigma bonds are very strong. Okay, so due to this large extent of head on head overlap for the sigma, it has a very strong sigma bond. Whereas if you take the case of pi bond, we know that this pi bond is formed by the side on overlap. Okay, this is formed by the side on overlap, and they are usually weaker than the sigma bond. So remember this point, it's very, very important that your sigma bond is always stronger than the pi bond. Okay, I hope this is clear to you. Now let us take the example of ethyne molecule to see that which bonds are sigma and which bonds are pi. So it is generally seen that in case of two atoms, one sigma bond is always formed first. Okay, so first of all, whenever a multiple bond is formed, the first bond would be their sigma, whereas the rest of the bond will be pi star. So this is being shown for the ethyne molecule. If you see, there are 4 sigma bonds, 2 with the hydrogen of carbon and 2 within the carbon, and that is resulting in a total structure of the ethyne. Okay, is it clear? Now in the ethyne molecule, if you look closely, then you can clearly see that 2 carbon atoms have a triple bond. You can see it here, that between these 3 groups of bond, we have 2 carbon atoms across it. And further, this carbon atom, which is triple bond, they will contain 1 sigma and 2 pi orbital. You can look at here. So whenever we form a carbon bond with the other, we first form the covalent bond and then we form the triple, you can say, first you form the bond, okay? Sigma bond, and then you form the pi bond. And you can see it very clearly here. So out of these 3 bonds, the first one is formed as sigma and the other 2 are pi. What about the other bonds that are being formed in this molecule? That is between C and H, and those are sigma. Okay. So we can say overall that in the ethyne molecule, we have 2 pi bond and 1 sigma bond between 2 carbon atoms and 1 sigma bond on each carbon hydrogen bond. So this was all for today's class. I hope you enjoyed the lecture. We will move on to the hybridization in the next class. Thank you.